Okay, so this is episode 2, part 2 of our webinar series on oil filtration. And it's one of 11 presentations that we're going to be doing. We've already done one. So this is number 2, measuring industrial cleanliness. So again, thank you for joining us. And it's a pleasure to have you with us. Really what we're talking about in this particular webinar, in this subject, is really how cleanliness is measured in an industrial application for lubricants. And so how we measure it, how we report it ultimately, and the differences between the standards. So there's a few things to talk about. I expect this is about a half-hour presentation. We may go a little bit shorter than that, but we'll get it over with as soon as we can. There is really 3 current major standards that are certainly being talked about. So there are three standards that I'm going to talk about in this presentation. Of those 3, one's almost irrelevant, but that's the way it is. We've set up a little poll. In the poll tab, we've got a question for you. I'm interested in which cleanliness classification method do you use most often? Now, if you're using one that isn't one of these 3 and you're using another one, I would love to know about it. You probably can't put that in the poll, but please put that in the chat and we'll have a look at it and we'll see what that is. But I would warrant that really one of these is more popular than the other, and we're going to describe the differences between them. Now, also, if you have any questions, please, we have a questions tab as well. If you could put your questions in the questions tab instead of the poll tab, that way we can see that it is a question and we can try and address that at the end of the webinar. Okay, so 3 major standards: the ISO 4406, the AS 4059, and the NAS 1638. We'll start with the NAS 1638 so we can dismiss it. Okay, so NAS 1638, the NAS is a National Aerospace Standard, first published in 1964, but it has been actually inactive since 2001. So if somebody is using that as a standard, they've probably not really seen that it's not really used anymore. And there's reasons for that. Ultimately, how the NAS standard works is that you're classifying the particles in a fluid by the size first. On the table, you can see that we've got the particle size in microns, 5 to 15, 15 to 25, 25 to 50, and so on. So what we're doing is we're classifying them in ranges and then counting out how many there are. And then within a certain range of numbers, you get a cleanliness class. So I've done a graph here on the right-hand side, and you can see how that works. And ultimately then the numbers then will just fall into that chart somewhere. So this is a standard that has fallen into disuse because the people that oversee the standards and the allocation of them have said, no, this one shouldn't be used anymore. Okay, but it's still a standard we hear of. We see it in books. Even some of our products still refer to it because there's still a market that is asking for it. Okay, so that's the NAS and how that one worked. It's basically been replaced by this one, AS 4059. So this replaced NAS 1638 in early 2005. So the SAE is Society of Automotive Engineers. They're the people that oversee the standard publications. So really, you know, this is an aerospace standard and it should be referred to as AS 4059. But for some reason, everybody refers to it as SAE standard. So it's a little bit confusing, but it's not too hard. This is by far the most current of the 3 major standards. I've had a look at it. It was reaffirmed 3 months ago, so May 2020. So that's edition F. So you can see 4059, A, B, C, D, E, F. And sometimes these get confused with the classes. But ultimately, the fact that this has been reaffirmed means they've looked at it and went, yep, that's still current, no need to change. Okay. I haven't been on that review committee, of course, but if somebody knows more about that and about the process of it, I'd love to know more. How the AS 4059 works is it's similar to the NAS. However, the principal difference is that the particles aren't classified in between a range between that and that size. It's greater than a certain size. So you can see here that is particles greater than 1 micron, greater than 5, greater than 15, 25, 50, and 100. And then the class coding is allocated to numbers for each of those ranges. Now, those ranges get labeled A, B, C, D, E, and F. So I've graphed that out on the right-hand side here so you can see how that works. Ultimately, you're going to be looking at particles in the red class, A, in the blue class B and class C, D, E, and F, and allocating counts and numbers within those standards. And you can see that these really flatten out as you go over to the right, meaning that as you have larger particles, you expect to see a lot less of them. Okay, so for example, the class F is particles greater than 70 micron. You'd really want to think you have not too many of them in a system. Okay, so it's replaced the NAS 1638, and primarily because it's easier to use and easier to apply, because it's particles greater than a certain size. You don't have to stop counting and recount at a certain size as well. So the classification of the particle is easier. Okay. The third and the most common is ISO 4406. So this is an international standard, ISO, and this has been reaffirmed 3 years ago. So the latest standard for this is ISO 4406 2017. Now, I've looked into the differences between 1999 and 2017. Not much. I suspect it's a font change. It's a bit more than that, but it doesn't affect really anyone who's been using a report from the 1999 standard for the last 20 years. The count, the number, nothing changes really with the new standard. There's just been some minor corrections. What's happened with this standard is really over the life of it, there's been two principal uses and principal additions of it. So it was the first half and the second half of its life. And I can classify them as being different eras in that standard because of this. In the earlier two versions, the contaminant that was used to evaluate filter performance was ACFTD, that's air cleaner fine test dust. Okay, and the way that a particle would be evaluated, say for example, you had a irregular shape like I've got on the screen here, then it was the longest chord, and the longest chord is really, how long that is at its longest point. With the new standard, and it was changed because the test dust had to change. With the new standard, it's not longest chord measurements anymore. It's basically a sphere of equal average size. So essentially you grab that particle and you melt it down like into a blob visually and say, okay, well, that's about that size. And it actually makes it easier to count and classify anyway. But importantly, the reason that changed was the contaminant, the test contaminant changed. So we don't use air cleaner fine test dust anymore. It's ISO medium test dust. There's a fine test dust and, of course, test dust as well. Now, if you are looking at a standard that is using the current 1999 and 2017 standard, the C in brackets is put after the number. So say, for example, you're looking at particle sizes greater than or equal to 6 micron, then the little C there that you may have seen, that means it's calibrated to the new test dust version. Okay, so ISO 4406, I've done a little chart here to explain how that works as well. Ultimately, it is the simplest one of the three to apply. Now, what you've got then is essentially a number that doubles. Okay, so we go 2 to 4, 4 to 8, 8 to 16, 16 to 32. There's a few little tweaks and adjustments in there, but ultimately the number doubles and the range doubles every time that there's a number. So what's going to happen then is this is a bit of an odd thing to visualize, because down low with the low numbers, we're looking at particles, 4 and 8 particles and between 8 and 16 particles. And at the other end of the scale, for typical lubrication and so on, we're talking about 16 million to 32 million particles. So it's quite an exponential thing, and it's very difficult to visualize. And just to try and show you how it works then, I've done this graph here. And you can see here that this is quite flat down here from the 1 to 14. But if I change the scale, you can see there's 4 to 14 there. And it's exactly the same. And it just keeps on going like that down to a class 1. Now, ultimately what's going to happen then is each number is half. If you go down in numbers, each number is half of the range of the one before it. So what you're going to tend to see in practice is that as you're filtering, as you say, for example, you're flushing a system and you're filtering the contaminants out, it's going to take a long time for you to see any changes as you're bringing a lot of particles out of that system. But then as you get cleaner and cleaner, your particle range, the number that you're in, will change more rapidly. And that's just the nature of it, because that's how the numbers work. Okay. So that's ISO 4406. Now, ultimately, it's the most common one for two reasons, according to me. Number one is it's ISO, it's international. So this is used equally in Europe and in North America, and of course the rest of the world. Number two is it's the easiest to apply, because it doesn't matter what size particle you're evaluating, you use the same chart. There's only one range that's used across the particle sizes being evaluated. So from that perspective, it's easier to use. Now, in my experience as a trainer, I see a lot of people, which is fantastic, and I am aware of the knowledge that people have. There are not many people in our industry that can really describe this in any meaningful way. However, it is something that everybody understands because it's easy in application. In application, it's basically like golf. Everybody knows how golf works with regards to scores. Basically, the lower the better. The lower the number, the better. ISO 4406 is like that. Okay, it's just easy to apply. So it's probably one of the reasons it's so popular. Okay, so we're on to part two. That's the numbers and how they're and the differences between them. We're on to part two, how particles are counted. So for this bit here, I'm just going to change screens and allow the video to play. Enjoy that. Okay, so what we're looking at is microscopic analysis. Then what we're doing is taking a sample of oil and we're pulling it through a membrane such as this one. And that membrane is basically going to act like a filter. It's going to remove all of the particles greater than, say, 0.8 of a micron. And it's going to allow us to then place it under a microscope and have a look at that. So it's essentially being demonstrated here with a pizza dish. And the contaminants, I've got mince. All right, so ultimately, of course, the dirtier the fluid is, the more mince I will see across my patch. Now, ultimately, I could just say, look, this is how many particles I have. But you know what? It's going to be more useful to me if I know the particle distribution. How many small particles, medium particles, and large particles? That's going to be better information, and I could be more equipped to make a decision. So I've got different size particles in here. So I've got really small ones. I've got some larger ones. I've got some larger ones again. And I've got some terrifying big chunks that look quite damaging to our system. All right. Now, there's two ways of looking at this. The first way is with microscopic analysis. Microscopic analysis uses the size designations of 5 micron and greater and 15 micron and greater. So for the purposes of the exercise, I will say that that is a 5 micron particle, or say 6 is greater than 5. And we'll say that that's about a 18 or 20 micron particle. So that's going to be the sizes. Now, ultimately, if I am looking at particles greater than 5 micron, then these little ones get excluded. It doesn't matter how many I have on here. It doesn't matter how many I have in my system. They don't get counted. They don't get reported, okay, because they don't meet the grade. Ultimately, that should be okay because, generally particles that are 3 micron, 4 micron and smaller are not very damaging to the system. Okay. Then particles that are 5 micron and greater, as I said, this is probably a 6. So I'm going to count particles greater than or equal to 5 micron. I will count every one of them, and every one of them on my dish. Every particle that isn't that size gets counted, but all of them get counted. For my next group, I've got particles greater than 15 micron. So I won't count that if that's maybe 6 micron. And if that's maybe 9 or 10 micron, I won't count that. I will only count particles greater than 15 micron. So if this is around about, say, 18 or 20 micron, I only count them. Okay, so I get the two classes there. Now, further to that then, if I'm doing a measurement with automatic particle counter, and that's what you're going to get if you send your sample to a lab, or of course you use a HYDAC particle counter, which is ultimately the same bit of kit actually. What you're going to find is the sizes are different, the classifications are different. It's greater than 4 micron, greater than equal to, that is, greater than or equal to 6 micron, and greater than or equal to 14 micron. Okay, so the same thing occurs. So ultimately what you're going to see is that gets excluded. The first count has a high set of numbers, a high count. The second count, you count less, and the third count, you count less again. So what this means is your sample report will have decreasing numbers, such as, say, 16, 15, 13, something like that. If you are seeing the same figures in 2 or more of those counts, there's probably something wrong with that sample, because that shouldn't happen. It's statistically impossible. Okay, I'll just throw them back in there. One final point. In this case, I've used mints, and the reason for that is the size is the only thing that gets evaluated. The material doesn't. So it doesn't matter if these are particles of steel or bronze or rubber or wood or some organic material. It doesn't matter. It doesn't matter at all, because we are only evaluating size with these tests. So whether it's an NAS sample or an SAE-AS sample or an ISO sample, it's actually size is all that matters. So in this case, they're all white, and we can think of them as only size. The opposite argument is, say, for example, these are M&Ms. So M&Ms, you could classify them by colour. But in this case, and with M&Ms, they would all be the same size. Okay, so it's not the same argument. So that is a little bit of an insight into the particle dropout and to what we're trying to do actually with one of these tests. Okay, thanks for listening and watching. Okay, so hopefully that made a bit of sense to everybody there. Okay, so ISO 4406 then, again, we have automatic particle counting and the optical microscope. And that's one of the things also that's very good about the ISO 4406 is it actually enables the use of both. Okay. Now, a little bit into that, as a little more information on that, as I said in that video. If you are reporting with an automatic particle counter, then that's how to do it. It's particles greater than or equal to 4, 6, and 14, because they're the ranges. And the C should be used if it's a modern, a 20-year-old system that's calibrated to the new test dust and the new method. The microscopic analysis is not sized the same way. It's still 5 and 15, like the previous versions of the standard were before 1999, like 1987. So they get reported 2 different ways, but also the first size reported as a dash if you are using a microscope. Okay, looking at the automatic particle counter, that's how this thing will be reported. As you can see, it's not just a visual output, but of course that goes to some data logger or something like that, Industry 4 connected device, and you can look at the cleanliness count of a system remotely. An automatic particle counter works on the principle of light obscuration, and that is simply magic. The particles go past a little sensor. The channel that the fluid's flowing through is about 1 millimeter wide. This thing is basically looking at how obscured the light source gets in the back. And of course, the more particles you have and the larger particles you have, the more obscured that result will be. How that actually translates into an ISO standard, that's the magic. That's where the magic happens. And that's the technology that's very, very clever. But it is frightfully accurate because they're designed to be that way. Optical counting with a microscope, how that's done is according to ISO 4407. So ISO 4407 is really the instructions of how all of this is done. And so, that is determination of particulate contamination by the counting method using an optical microscope. There's your instruction manual, ladies and gentlemen. Basically, it's reported by ISO 4406 and informed by ISO 4407. That's the test method. Got another quick video. This goes for about 30 seconds. There's no sound on this, but I'll talk through this one. Ultimately, when we are taking a particle count, we are going to see a video here, hopefully. So what you do is you are going to be passing fluid through a membrane. Then the membrane is going to catch all those particles if they're greater than a micron, and you're going to be able to put that under a microscope and evaluate it. So I've just got a very quick video here of how that works. There is no sound on this one. Hopefully the video works. Okay, so we use an ultra clean solvent here. The ultra clean solvent is filtered to a very, very fine particle size. You're evaluating 100 ml of the lubricant. You're using the clean solvent to flush it through, and then you put it under a microscope. Something happened to that video. I'm very sorry. So once you have that little patch, you put it under a microscope and you can evaluate it. The easiest way to do that is to use a comparator, and there's a little publication that HYDAC have, a little fluid contamination handbook, and these are verified images of those cleanliness classes. So what you can do is just basically have a look at it, and it's that fast. You look at the patch over 4 or 5 places, and you say, okay, it looks like this. And don't know if you can see on your screen, but each of these is a particle size one up from the one below. So there is a visual difference between them. The easiest way to actually do this is just optically. You just look at it and say, it's that clean or that dirty. And my experience is that that's how most people who use our patch test kit and their microscope actually come up with a number. My experience is most people don't actually count it. But if you were to count it, ultimately how that little technology works is you know the size of the area that the fluid has been filtered through. And there's a method in 4407 about how that's established. So you know that size, and you know the size of what you're evaluating, whether it's a square area because you're looking at a microscope camera and viewing it on a PC, or a round area because you're just looking through the optics of the microscope, or you could use a patch grid if your grid has patches. Patch has grids. You are calculating that area as a representative sample, and you count a number of areas. And what you do then is you say, look, this many areas had that many particles, therefore the patch at that area will have so many particles, and it's done by a calculation. So if you're wondering if you are going to be counting 130,000 particles, you're not. You're going to be counting an average represented area of that, and that's how that test is done. It's remarkably simple, but also quite technical, and there's a lot of things that you can do wrong that will change the count. And the most important thing to get right is how that sample is taken. The way the sample is taken in the first place affects the count more than anything else. Okay, so hopefully this has been a bit of an insight into how all of this works. As I said last week, there's a lot of interest in filtration as a subject. So this has been episode 2 of 11. We'd love to have you join us for some more of that. The next one that I will be doing is evaluating filter performance. Thank you for your time, and everybody stay safe. Thank you.